Hi everyone, in this video we are going to discuss about theorem number 21 from the geometry of circles. The theorem says, in a circle, the bisector of the angle between two equal chords drawn from a point passes through the center. Which means, if we draw two equal chords from a point on the circle, and then if we draw the bisector of the angle between the two chords, then the bisector will go through the center of the circle. Let's suppose we have a circle like this. The point O is the center of the circle. And let's suppose we have two equal chords like this. Both of them are drawn from the same point A. So AB is equal to AC. And then I'm going to draw a bisector of the angle included between AB and AC, that is the angle CAB. So if we draw the bisector of that angle, let's suppose AD is the bisector of that angle, we have to prove that AD goes through the center. That means AD is a diameter because that is the only chord that goes through the center of a circle. So somehow if we can prove that AD is a diameter, then our theorem will be proved. So for a moment, let's pretend that we don't know if AD goes through the center or not, right? Now for the proof, I'm going to do a little more construction here. I'm going to join B with D and also I'll join C with D. Let's assume that angle CAB, the angle between the two equal chords, is equal to 2 times alpha. Then each of the little angles there, the angle CAD and the angle DAB, they will be equal to alpha. Each of them will be equal to alpha. Because AD is the bisector of the angle is assumed to be 2 times alpha. So if we bisect that, each piece will be equal to alpha. Also in a previous theorem, we have seen that equal chords subtend equal angle in the alternate segment. So here if we think about the chord AB and the angle ADB is a subtended angle for that chord, and similarly for the chord AC, angle CDA or angle ADC, that is a subtended angle, and because the length of these two chords are equal, that means they will subtend the equal angle there, and let's assume that angle to be theta. Now let's take a look at these two triangles there, the triangle ACD and the triangle ABD. If we look at these two triangles, you will see we have two pairs of angles there equal between the two triangles, and also the common side, which is AD, that is common between the two triangles there. So using the ASA criteria of congruence, we can say that these two triangles are actually congruent triangles. In fact, we could have proved it the other way also, because AC is equal to AB and AD is a common side and angle CAD is equal to angle DAB. So using the SAS criteria also, we can say that these two triangles are congruent triangles. And because these two triangles are congruent triangles, then the only remaining angle, which is the angle ACD and the angle ABD, they also will be equal. And let's assume that that angle is beta. Now if you look at the diagram, clearly ABDC, the quadrilateral ABDC, is a cyclic quadrilateral. In a previous theorem, we have seen that the sum of a pair of opposite angles in a cyclic quadrilateral is equal to 180 degree. So for this cyclic quadrilateral also, we can make the same claim that the angle C and the angle B, their sum will be equal to 180 degree. And that is nothing but beta plus beta is equal to 180 degree. That means 2 times beta is equal to 180 degree. And that means beta is equal to 90 degree. In a previous theorem also we have seen that only a diameter can subtend a 90 degree angle on the circle. And here, because the chord AD is subtending an angle of 90 degree, which is the beta angle, that means AD is nothing but a diameter of this circle. And that's exactly what we needed to prove. And because AD is a diameter, definitely it passes through the center of the circle, and that's what we needed to prove for the theorem. It is a very important property of circle. Please make a note of it. I hope the proof made sense. Thank you for watching. See you in the next video.